Three formulas to
Yeah, so 3 formulas you have to remember about heat capacity and specific latent heat. The first one is it totally depends on what is given in the question. Like some questions, there's a change in temperature, so energy E is equals to Cm delta T. This formula is valid if they mention there is a change in temperature. To calculate the heat energy, if there is a change in state, like a solid turn into a liquid turned into a gas, so mass into latent heat, and this formula is valid if in a question you have a change in state. And there's also another formula that energy is power multiplied by time, and the power is actually a product of voltage and current, so we can also say
electrical
energy,
heater.
yeah, electrical heater. So energy is V into I into T, where V is the voltage and I is the current. So this formula is valid if you are using a heater. What is the meaning of a C? C refers to the specific heat capacity. This we did in the last session. So C refers to specific heat capacity. And what is L? L is the specific latent heat. And where P is the power, V is the voltage, I is the current, and T is the time. So these are the three main formulas which we'll use to solve these questions, the exercise related to the specific heat capacity and specific latent heat.
Assalamu alaikum.
So the first 8 questions I already solved. So I will start with question 9 and we'll do 9 onward. The first one, a silver spoon has a thermal capacity of 7.2 joules. This topic, thermal capacity, is not part of the syllabus like 2023. So we'll not discuss this. So we'll skip part A. The next one, a silver spoon is dropped. Part A and B actually are related to the thermal capacity. So we will skip both of them. And B2, state in terms of atom what is meant by internal energy. What is the definition of internal energy? How we define internal energy?
The energy inside the lattice.
Energy inside the lattice, or you can also say the sum of energy, sum of kinetic and potential energy of the particles. So the complete, yeah, it's same like the total energy of the lattice, but because it's of 2 marks. So how you score 2 marks when you mention total energy of or the sum of kinetic and potential. 1 mark is for kinetic, 1 mark is for potential. So the sum of kinetic energy and the potential energy of the particles is refers to internal energy when we add the total energy of all the particles. Is it clear?
Yes, sir.
Yes, sir.
The next
Yes, sir.
part, in the next part, the spoon is removed from a boiling water. So like, say there was a container which was filled with the boiling water. So what is the temperature of a boiling water? The
100.
water is
100 degrees.
100. So 100 is the temperature of a boiling water and there's a spoon inside. What we do, the spoon is removed like, so what is the temperature of the spoon? Because it was there in a boiling water, it will also be 100. Then we remove the spoon outside and the surrounding temperature is 22. So what will happen? Like the spoon will start to release or give out energy to the surrounding until it reach a thermal equilibrium, like the temperature of a spoon will be same as the temperature of the
Equal
surrounding.
temperature.
Equal temperature. So on figure 5.1, sketch a graph to show how the temperature of a spoon changes with time from an instant that is removed from the water. It's of 3 marks. It's very simple. Like first, you don't have to draw a straight line
Straight
because
line.
no, not straight line. Because if you draw a straight line, it means it is losing energy with the same rate. In the beginning, it is losing faster, but when it cooled down, like as the temperature is decreasing, the rate of energy loss is also decreasing. So it will be a horizontal. In the beginning, it's steeper. It should not be a straight line. If you draw a straight line, what does it mean? Like it is losing heat energy with the same rate. But practically, it's not possible. When the substance is hot, it loses more heat energy every second as compared to when it is at lower temperature. So when you sketch a graph, it should be a curve starting from 100. It should end around 22 and horizontal line around 22. Is it clear?
Yes, sir.
Figure 4.1 shows an apparatus used to measure the specific heat capacity of iron. Look, to calculate the specific heat capacity, the student improved the accuracy of the experiment. What is the equation to calculate the specific heat capacity? So to calculate the specific heat capacity, look, the formula which include the specific heat capacity, energy is equals to Cm delta T. So if you need a specific heat capacity, like specific heat capacity is a subject, so energy divided by mass and temperature change is equals to specific heat capacity. And practically, as we are using an electrical heater, so what will be the energy supplied? How we know how much energy is supplied if electrical heater is used? So that is
Voltage.
voltage into current into time or power into time. Practically, like power into time or voltage current into time. So in place of energy supplied, whenever we are using a heater or electrical heater, energy supplied is voltage into current into time divided by mass into temperature change. So we have to measure the voltage, we have to measure current, we have to measure a time for which we supply heat energy, the mass of the block, and the temperature change of this block. Now we'll solve the question, the part. This was just an introduction of how to work out specific heat. The student improved the accuracy of the experiment by placing a material around the block. As you can see, first there was nothing around the block. But then student place a material around the block, suggest the name of the possible material that student could use, and explain how to improve the accuracy of the experiment. Basically, yeah.
Use insulating material so that the heat energy wouldn't be lost to the surroundings.
Good. So student use in any suitable insulating material you can mention, like you can mention cotton, you can mention cardboard. So suggest the name of possible insulating material. So it is like a cotton. An explanation is that it does not allow, like why it's of 3 mark. 1 mark is for mentioning that the name of the insulating material. The second mark is for because the insulating material does not allow the heat energy to escape. So we'll get an accurate amount of energy supplied to the heater, supplied to the block. So cotton, and then explanation, insulated, like it does not allow the heat energy to escape. So the energy supplied by the heater equal to energy absorbed by the block. Otherwise, when a heater is supplying energy, Is it clear to everyone?
Yes, sir.
Yes, sir.
Sir, can we say copper or no?
If you mention copper, copper is a conductor. Conductors, so what they will do, like example, if I surround this by a copper, the copper will take the heat energy, like because like this was surrounded by a copper. So when the heater supply energy to this solid, that will transfer energy to the copper. So copper will take that energy. But if it was like cotton was there, it is not allowing that energy to escape. So any insulating material you can mention, cotton, wool, cardboard.
Sir.
Yes.
Sir.
The next state, how the student could further improve the accuracy of the experiment by using more of the material in figure. Can you identify which point he is missing the material?
Yes, sir. He's inserting material on top to cover
On
the.
top. So he did not put the insulating material at the top, so he should cover the top of the block also with the insulating material. Because it should be all around, not it can lose energy from the surrounding, from the base, like from the sides, from the base, and also from the top. In this question, the current in the heater is 3.8. So we have current or I. The potential difference is 12. That's V. The block has a mass of 2 kilograms. That's M. The heater is switched on for 10 minutes. Whenever time is given, time should always be in seconds. So 10 minutes, you have to convert into second. You multiply by 60, so it will be 600 seconds. The temperature rise or changes from 25 to 55. Calculate the specific heat capacity. Because if there is a change in temperature, you can see the temperature changes from 25 to 55. So which formula we should use whenever there is a change in temperature?
So the energy is equal to what is it called?
C,
Specific heat capacity
into mass into temperature.
Into mass and temperature change.
Yes.
Why it's a 4 mark? Whenever a question is normally a 4 mark, it means you have to use 2 formulas in that question to solve. Like this is just an idea from the mark. I have an idea that because it's a 4 mark, so definitely there are 2 formulas you have to use. First is E is equals to Cm delta T. So we have we have to find the specific heat. We have the mass. How much is the mass? That's 2. And the temperature change, it changes from 25 to 55. So difference will be there. 55 minus 25, which is equals to 30. But what about the energy? How we can work out the energy? As we
Power
have
into time.
Yeah, power into time. Energy is power into time, but the power is not given. Voltage or currents are given. So it is voltage into current into time.
Yes.
So voltage is 12. The current is 3.8. The time is 10, but should always be in seconds. So 60. What's the answer for this? 12 into 3.8 into 600. Twelve into 3.8 into 600.
27,360.
27,360 joules. That is the energy. So this is the energy we supplied. So E is there, which is 27,360. Now we need the specific heat capacity. So this 2 and this 55 minus 25 is 30 actually. So I can just write 30 here as a temperature change.
It will be 60, then 60 the other side divide, then it will be
yeah, so it will be 27,360 divided by 60.
Divided by 60, 456.
So 456, and the unit of the specific heat capacity is joules per kilogram degree centigrade. That's a unit of specific heat capacity. Is it clear, this part?
Yes.
Clear, okay.
Yes.
In question 11, a student is supplied a small block of an iron, a thermometer, and a heater of power P is there. There are two holes drilled into a block, as you can see. So two holes are drilled into a block. One is for placing a thermometer, another one is for the heater. And the block of iron is there. The student uses this equipment when determining the specific heat capacity. The other equipment the student will need, measurement the student need, and equation student when calculating the specific heat capacity. So power is already known, but to calculate a power, we can also have, because to calculate the specific heat capacity, specific heat capacity is energy divided by mass into temperature change. And energy, practically, it's a product of voltage, current, and
Voltage
time.
into current.
Energy is power into time, and power is voltage into current, and mass is there, M. And temperature change, final minus initial. So first, other equipment, what student is already having a thermometer. That is one is already there. What
So
else
a
student
voltmeter
needs?
An
to-
insulator.
Insulator is to improve. It's like for improvement, he should insulate a block so it will not lose energy. But the first part of a question is what other equipment, like you can mention, but the main thing is like insulation, make it better, like you get an answer closer to the true value. But what other apparatus we need, equipment we need? So first
voltmeter
thing,
to measure the voltage.
so we need a voltmeter because voltage can only be measured by a voltmeter. Current,
Ammeter,
ammeter, then time,
stopwatch,
stopwatch,
mass,
then mass,
balance.
balance, stop and balance. So why we did not mention thermometer? Because they already asked for other equipment student needs. So this is the answer for the part. Measurement student need to take. So what student has to measure to calculate the specific heat capacity?
Sir, energy.
But energy is not like measure. Look, energy student will calculate. That's fine. But what he will measure, the measurement. So what he will measure, he will
Temperature
measure.
change.
He will measure.
Temperature.
Yeah. First thing, you start with a numerator. So voltage is there. So he will measure a voltage, current, time for which heater is, time for which heater is switched on. And you don't mention, because we don't measure the temperature change, we calculate the temperature change. What we measure is the initial temperature and the final temperature. So we'll measure initial temperature, because they're asking for measurement. They're not asking what you will calculate. We'll calculate the temperature change, but we measure the starting temperature or the initial temperature, and we'll measure the final temperature. Is it clear? The things, actually both answers
Yes.
are related to each other. And then the last part, they ask for equations. So what equation you will write? You can write this equation, that energy, the specific heat is VIT divided by M into the temperature change. A similar question is there. It's mainly like most of the questions are either like calculation of the specific heat or the practically how it can be done. So figure 4.1 shows some of the apparatus that student used to determine the specific heat capacity of aluminium. You can see here, insulation is also used here. What is the purpose of insulation? That it prevent the heat loss. So we'll
Trap
get a more,
heat.
trap the heat, does not allow heat to escape. So we get a more accurate result. State the measurement student need to make, include those from electrical circuit, and for each measurement state the symbol. So it's the same answer. Like there's no difference. So
Symbol.
yeah, same, and we will use a symbol like here voltage is V, current is I, time is T, temperature 1, initial temperature T1, final temperature T2. So measurement student need to make what student here, but only difference is that we don't need the for each quantity measured include like what we have to measure. We have to measure voltage, current, time, initial temperature, and final temperature. And then we include a state symbol as well, like the equation symbol. So it's the same answers. It does not make any difference. An object of mass M, specific heat capacity C, supplied a quantity of a thermal energy. Write down expression of a C in terms of Q. Some because and delta theta. What does it mean? Delta theta means temperature change, and Q means energy. So how we can find and how we can write an expression for C in terms of QM? So we have energy E is equals to Cm delta T. If I want the subject as specific heat, so specific heat is E divided by M delta T. So E is actually energy, which is Q represented by Q. So I'll write Q. M is the mass, and temperature change instead of delta T, that increase in temperature is delta theta. So we can write delta theta. So this is what we have to write. The same equation, but we modify energy is given by Q and the temperature change is given by delta theta. Is it clear, this part?
So I still don't get it.
Okay. Look, we have, the question is we have to represent the specific heat capacity. The formula, whenever there's a temperature change, we have the formula E is equals to Cm delta T. Okay. In the question, they are saying the energy supplied is Q and the temperature change is delta theta. So we need an expression in terms of for the subject C. Like if you want a specific heat capacity, we want to modify this equation in terms of Q and delta theta. So what is the energy supplied here? The energy supplied is Q. Specific heat capacity, we don't know. M is a mass. And what is the temperature change? Instead of delta T, they mentioned the temperature change is delta theta. So we write delta theta. Now, if I want to make subject as a specific heat capacity, so mass and temperature change are multiplied, other side it will be
So
divided.
Q over M delta Q.
Delta theta. This is a Greek alphabet. It's like a Q, but it's a Greek alphabet, which is theta. So it means the specific heat capacity is Q divided by M delta theta. Same thing. They ask for this expression for C in terms of QM, and so we write that C is equals to Q divided by M delta theta. That's it. Clear?
Yes, sir.
In part B, figure 4.1 shows the heating system of a hot water. The power supplied is there, a cold water enter and the hot water leave. This is what happened in a geyser. So cold water at 15 degree flow in at a rate of 0.0036 meter cube per minute. Like every minute, this much amount of a cold water enter and same amount will go out. Calculate the mass of a water every minute if the density is 1000. So we have the density and we have the volume. How we can use the equation to find the mass? So density is mass over volume. If I need the mass,
Density times volume.
density times volume. So density is 1000 and the volume is 0.0036. So when we multiply, it will be 3.6 kilogram of a water will flow every minute. Like in 1 minute, this much mass of a water will flow through this heater.
Yes, sir.
So we were having a density, we have the volume. That's how we work out the mass. So 3.6. The next part, the power is given, which is 8.5 kilowatts. So it means 85
joules energy.
8.5 kilowatt means 8.5 into 10 to the power 3 or 8,500. Yeah. So we have the power. Calculate the temperature of hot water. We want the temperature of the hot water, like at, say, the starting temperature, this was 15. We need the final temperature of the hot water. At what temperature the water is coming out from this heater. And because it's every minute, like in 1 minute, how much temperature change happens from 15. So whenever there's a temperature change, what is the formula for energy? The energy E equals, as there is a change in temperature, so E is equals to Cm delta T.
Mass times
Mass, specific heat times mass times temperature change. Now, specific heat, this is the specific heat capacity, which is 4,200. The mass of the water, this was, we already calculated, this was 3.6. So mass is 3.6 times the temperature change. The final temperature we want, the initial temperature is 15. So it is T2 minus 15. Why? Because like when it entered the heater, it was 15. When it leaves the heater, that is what we have to find, the final temperature. How much energy is supplied? So whenever an electrical heater is there, energy supplied is either power into time or voltage current into time. So power is 8.5 kilowatt or 8,500 multiplied by time, because it's every minute, 1 minute is their time. So 1 minute, how many seconds will be there? 60. So we multiply by 60. So what is the energy? How much is the energy supplied? So 8,000.
510,000.
How much can you say?
510,000.
510,000. Joules. From where I got this 15, if you see the question, they mention a cold water enter at a temperature of a 15. So the initial temperature or temperature of a cold water is 15. And it leaved, that we have to find. That's how I got the 15 here. The temperature of a cold water is 15. The initial or the starting temperature is 15. So now we simplify to calculate the final temperature. So this was 510,000 joules. Now simplify 4,200 into 3.6. What's the answer? 4,200 into 3.6.
15,120.
15,120. And this is 510,000 into
Yes,
T2
divide.
minus 15. This factor is multiplied, other side will be divided. I'm using this space. So 510,000 divided by 15,120. What's the answer for this?
Sir, 33.7.
So this is 33.7. So 33.7. And then because we need the final temperature, it's like the temperature change is T2 minus 15. So it's minus 15, it will go other side. So it will be 33.7 plus 15. So it will be 48.7. So final temperature of the water will be 48.7 degrees. So the water entered this region. When a cold water entered, it was 15 degrees. After 1 minute, when it leaves, it is 48.5 degrees. When the power of the heater is 8,500 watts and the water remain in the heater for 1 minute. And how much water will flow every minute? That is 3.6 kg. Is it clear, this example?
Yes, sir.
Yes.